Hello, people. All right, so here's our second installment on phasor circuits here. So I'm going to go right back to my OneNote, and let's just briefly talk about what we said, what we did last time. So what we did last time is we did something like this here. We went in and we looked at solutions here. Well, what we're doing here is that we're starting with our standard solution for a sine or cosine type source. And so we have a natural and a forced response. And we say that if we reach steady state analysis, then that means here that that the um, that the natural response always decays. So in AC steady state, we only care about the force. And one of the things that we said here is that when we go and we look at the solutions here, the solutions that we dealt with, let me see if I have it up here, that we dealt with up to this point here is that it was B1 times cosine omega t plus B2 times sine omega t. And what I said here is that when you go to AC steady state, this is not a good solution to have. What is a good solution is to move these two arbitrary constants, B1 and B2, which is what I call my forcing constants, into a single amplitude and a single phase. Because once you set the frequency of the circuit of the function generator, omega t will never change unless you pick some particular time here. So it's more appropriate to put the constants in A and theta here. And at the end here of last time, we ended up showing here is that when you do a solution like this in AC circuits, we find that the amplitude is frequency dependent. Actually, we did it up here. Sorry. We find that the amplitude is frequency dependent and the phase was frequency dependent. And this is much nicer to deal with than if you deal the solution that's B1 cosine omega t plus B2 sine omega t. And the reason why that is that now I have two amplitudes that I have to interpret that are frequency dependent. Whereas here, I only have one amplitude. So if I focus on one amplitude, we said here is that as the frequency increases, we saw that the inductor acts like a short, which is, excuse me, as an open, and that doesn't surprise us because we know from physics 4b that if I change the frequency of the function generator, very, very fast, the back EMF of the inductor gets so huge that it just kills all the current in the circuit. And if there's, and we also saw that there's this phase factor of theta that's frequency dependent. And we see that at high frequencies, this phase goes to 90 degrees here. Now, does that mean anything? Not necessarily. All I'm trying to say here is that if you look at just the amplitude and the phase, it's easier to interpret than if we use the chapter 7 and 8 solution forms. And so now what we did is that we said here is that now we're going to take the solution from chapter 7 and 8. We now moved it to a solution form that looks like this. And my main goal here was that no matter how you slice it up, if you have a circuit that's AC, I can deal with two amplitudes, B1 and B2 being frequency dependent, or I could deal with one amplitude being frequency dependent. But the cost is that now I have this angle, phase angle, that's frequency dependent. And the fact is that it gets easier to interpret this if we now go to the easier form of the solution, which is phasor form. And like I said before, a phasor is just a nickname for a vector in the complex plane. So now what I'm going to show you here is that There is an omega t term here. It gets suppressed because it turns out that it's going to be on both sides of the equation. What is going to be different here is that this x of m is the amplitude, which is replacing this a, and then this theta is the same theta here. And so we only then focus on phasors, to really amplify the role that the new amplitude and the new phase actually do that here. And you know what? I screwed up. I forgot to put in an applet. Let me go get that applet set up because I'm going to need it. So let me just set this up for when I'm going to need it here in a moment. Okay, now I'm set. So we did some regular properties of complex analysis here. And I said that these two right here, Euler's relationship and these two forms of J and -1 become immensely important in phasor calculations. And what I told people, I said, just memorize the damn things. You should always have these memorized anyways. They just pop up in life all the time. Now we're back to where we start now. So our goal here is to go in, and our job here is to now move towards phasor relationships now. And here we go. And what it comes down to is that we really want to write things in terms of the language of Ohm's law. How we derive anything with simple relationships is that. So what we want to look at right now is that we're going to look at phasor relationships of R, L, and C. And what's going to be really important here is that Ohm's law is the driving engine for this whole thing. So here we go. So what we've said here is that we've converted solutions for AC steady state. And pretty soon, I'm never going to say AC steady state again. It's just going to assume that that's the case, right? As soon as you turn on your function generator, the system's already in AC steady state, just like you saw when we were looking at the circuit for RC here. So we've converted solutions for AC steady state of the time domain. And so when I'm thinking about the time domain, what this means here, when I say that, that means I'm going to get a cosine of omega t plus theta. Okay? Where now we will transform them it's probably more appropriate to say transform them to the frequency domain. And in the frequency domain, you're going to see here that it takes on the following form. I'm now going to have a complex vector, and it's going to have an amplitude, and it's going to have a phase where I get e to the j omega t. So note that I could have written this like this. So then I get j omega t plus theta. And you could see how this guy right here, that argument, is the same as that argument. But the important thing here is that this quantity is our phasor vector. Okay, so what we want to do here is that there's a reason why we move into the frequency domain. There's a reason why we get our phasor method. It just makes life so much easier, okay? It just makes life so much easier. So what I'm going to do here is that I'm going to just take a very simple step, okay? And when I think about this simple step, what we're really doing here is that we're going to really just do some simple mathematics. We're going to go back and we'll look at some circuits here. And all we're going to do here is that in order to really do this, we have to take our regular circuit in the time domain, and you're going to have to convert it into a phasor circuit, which is different. And when we do that, you're going to see that we have to rewrite our components, R, L, and C, and it could be sources too. We have to write them into their complex form, and from their complex form, we're then going to apply KCL, KVL, whatever it is that you want to do here. And you're going to see that every time we do this, on both sides of the equation, we're going to get this e to the I omega t. And so this e to the I omega t will always cancel out. And because it cancels out, the only thing that's left in a phasor circuit is its amplitude and its phase. And that's it. And there's a very, very, very strong picture that I'll show you of an applet that really shows you what that actually means here. And then what we're really doing is that we're taking a complicated circuit, we're transforming it into the frequency domain / complex plane. We solve it there. Why? Because now it's a linear circuit with complex numbers nonetheless, but it's a linear circuit. And let me remind you, linear circuits are powerful, right? That means I could go back to doing series and parallel. And here's the catch: with resistors and inductors and capacitors simultaneously, which is crazy when you think about that. Think about that. I'm going to take resistors, capacitors, and inductors and treat them on equal footings. Now that is badass. In the phasor form, you can do exactly that. So then we solve matrix equations again. We solve algebra problems again. No more differential equations. And then once we solve the algebra in the complex plane, we then transform back or map back into the time domain, which then, if you want, you can write the solution for that. And of course, the big role is Euler's relationship. So that's a really, really powerful thing here, right? So in summary, what I'm saying here, when R, L, and C get transformed into the complex plane, these elements are linear and can be treated with equal footing. And you gotta step back and just say, wow, how could that even be, right? A capacitor is an animal that's quite radically different than a resistor. Yeah, there is some characteristics of a capacitor that are different. There's no doubt about it. An inductor is quite radically different than a capacitor. But yet, in the phasor form, they're all linear. So no more differential equations. And that's really important. So for an RC circuit, that seems okay. Okay, so I don't get the first order equation. I don't get the first order differential equation. So what do I get? I get a series of maybe two equations, two unknowns, depending on the circuit. What if I have an RLC circuit? I don't have a second order differential equation anymore. I get a system of equations. But when you think the other way, what happens if I have two capacitors that are irreducible and one inductor and a resistor? That's a third order differential equation. What if I have three inductors and one capacitor? That's a fourth order differential equation. How do you deal with these things, right? The mathematics gets more and more and more complicated. But the fact is this, that if we transform this thing into the complex plane, all of the techniques that we use for mesh and node come back. And instead of solving a fourth, a fifth, a sixth, a seventh, order differential equation, which I have no idea how to do it. The only thing I would know is to shove that thing into a computer and pop it out. But in phasor form, all you do is you solve a system of equations. And then you could easily convert it into the correct solution with the seventh order differential equation. That is phenomenal. That is why people go after phasors. No other reason. Well, there's other reasons, but that is gotta be the most powerful one of all. So what I'm going to do here is that I'm going to apply this technique here, right? These three-step techniques here, and I'm showing you how, and I'm going to just show you some very, very, very basic things. And once it's basic, then what we're going to do here is that then I'm just going to go in and I'm going to start to look at this thing here. So here we go. Okay. And the first thing that we should probably look at is that we probably want to look at the resistor. Okay. So what I'm going to do here now is that I'm going to derive. We are going to derive the basic three-element Ohm's law equations for AC steady state. It's Ohm's law. Everything's about Ohm's law. And what you're going to see here is that from this thing, you're going to see here is that from Ohm's law form, what we're going to find here is that we know that this typically gives us the resistive nature of the element. Right? And I mean, just to kind of give you a sense of this, right? If I have some voltage and I have some current, I know that if I look at the ratio of V to I, this guy is the resistive element. And that resistive element is going to tell us how it behaves. Now, one of the things here, I should be a little bit careful. That's not the way we're supposed to write it. We should write it as current divided by the voltage, but I don't care. I really don't care. Okay? So here we go. So the first thing I'm going to do here is I'm going to start with the easiest relationship, which is, of course, the resistor. So I want to look at, here I go, AC resistors. what does it mean for a resistor to behave like in an AC circuit? And so what we do here is that the way we write it here is that we would do the following thing here. So ultimately, I'm going to have a resistive circuit. And when I say a resistive circuit, that means I'm going to have some AC circuit where this guy's going to be Vm cosine omega t. And I'm going to have some resistive element. And only a resistive element. And all we know is that there's a current here called IR going in that direction. Now what we're going to do here is that I'm going to stop writing this. And the way I'm going to write this thing here is I'm going to write this as V source. And then I'm going to equate this thing so that it looks like this. I now have an AC source, right? I should probably write a plus and a minus sign here just to remind you. And then I have my element like this. And again, this is the exact same circuit here. This is my time domain circuit. So the goal here is to do what? I want to convert the circuit into a phasor circuit so that in the end, this is what's going to happen. That now, the goal here is that there's a conversion factor. So I want to convert to a phasor circuit. Now, what you're going to see here for the resistor, it's not that big of a deal here because it's going to look almost identical, but there is a difference. Look at the difference here. The source now is not a scalar. It's a complex vector. So when I look at that, I have to put an arrow here. When we get completely into our circuit solving problems, I will never put an arrow on it. But for right now, I think it's important. We are now in the complex plane. And then I look at my thing here. And there's a new element here. It's not the resistor. We don't call it the resistance anymore. We call it the resistive, reactance. And I still, so that's would be my phasor circuit right there. And now check this out. This current is not the regular current. It is a complex current that moves in this direction like that. Ultimately, this is what we call our frequency domain circuit, but nobody calls it that. This is what we define as our phasor circuit. So one of the important things here is that we got to go and we got to look at this thing. So here we go. So now moving up here a little bit, I'm going to do some what looks like simple algebra, but it is. So what we assume here is that we know the voltage source, right? We know the voltage source and want to determine the ratio of V of M divided by I of M. That's Ohm's law. So let's go do this here. So of course, when we look at this thing for a brief moment, I'm going to have some polarity. And what we're going to say here is that if I apply KVL along this very, very, very simple circuit, what I should have then is that I have Vs must equal to VR. Right? That's our circuit right here. Now, when I look at this thing, I know that R is a linear element. Okay? So again, this is our time domain. But now what I want to do here is that I want to convert this into the complex plane. So now what I'm going to do here is that now I need to go into complex form. And so when I look at this thing, I now have a voltage form that's a vector. And I know that the resistor here, look at what I'm calling it, X of R. I could call it R too, by the way, should be equal to what? Times the phasor current. And here's the thing about that. I forgot to tell you, this guy is also a vector. So now what we do here is that then we look at the complex form here. So the complex form says this here. I take a vector, and the complex form is going to have an amplitude, and then it's going to have this phasor, this exponential solution here. So here I go. But the wait, it's omega t. And omega t represents, again, the source right here, right? That source is omega t. So what I'm going to do now is I'm going to plug it into this equation. And so when I plug it into this equation, what it tells me here is that here I go. Here's my amplitude of my source. Then it's going to be Ej omega t. Then I have my reactance. And then I have my I, and my I should be e to the j omega t. So one of the things that you see right away here is that this is my phasor solution to this circuit here. The first thing that you note is that look at the ij omega t. They're on both sides. So they cancel out. So now, solve for the resistive part. So in this case, according to Ohm's law, that tells us that V of M over I of M should be equal to X of R. And in this case, we know that X of R is just going to be R. So according to Ohm's law, this is what we have. This is Ohm's law here. Now you may say that, wow, really? You redefined Ohm's law for me. Thanks a lot, right? That means nothing. Well, it does mean a couple of things, okay? There's a couple of things that it means, and this is what it means here. What it means here is that, remember, we have sinusoidal solutions. And in this case, this implies here is that the voltage source and current have, oscillating solutions. So when I look at these solutions, what do they really tell us here? They tell us a couple of things here. One thing that they tell us here is that they tell us this here. There's a series of things that we should see here. So the first thing here is it tells us that that the amplitude of the reactance, the resistive, right? Reactance XR is equal to R. And what that really says here is this. This is not frequency dependent. It is not frequency dependent. So if I come in here and I plot X of R, which is R, as a function of frequency, what we know here is that this guy is not dependent upon anything. It's just a constant, period. So that's one thing that it tells us. The second thing that it tells us here is that when the current goes through the resistor, the phase between VR and IR are exactly the same. Now remember, we have oscillating solutions. So what that means here is that if I now go plot this thing, okay, let's say this is our plot right here. I'm looking at the waves now. So I have a voltage across the resistor. Let's say that this is the voltage across the resistor. Right? This is the voltage across the resistor. And it's oscillating. Of course it is. It's AC. Right? So this guy is VR. So when I look at this relationship, note there's nothing to indicate that there's a phase angle between V and I. Right? You know, I should have been a little bit more careful with my notation. Maybe what I should have said here is that since the voltage of the source is the same as the voltage across the resistor, I should have really done this instead. And that's a screw up on my part. So if you look at this thing, because there's no phase angle between these two here, that means that the current of the resistor through this thing, well, it has to be right on top of it, right? So that means this guy may be looking something like this here. The current's going to look like this. Oh, it's going to be looking something like this. It's in phase, right? So this guy's in phase. This is not a very pretty drawing, but but you could guess what I'm doing here. So this is the current of the resistor. So there's no phase difference between the current and the voltage. So what we say here is this, that the resistor does not change the phase of the current. So there's no phase change. So in other words, the phase of a resistor is 0 degrees. So now if I go and I look at the complex plane, okay? So if I look at this on the complex plane, what you're going to find here is that we have this here. We have a vector. This is J. And of course that this is the real axis. This guy here is the imaginary axis. And what you're going to find here is that the reactance is a vector in the complex plane. And that reactance has zero phase. That means then when I draw a resistor in the complex plane, it's a vector that points in the real, because this guy has an imaginary number of 0. This is what we do then. That is our picture. And this is the start of a phasor diagram. Okay, so now I've talked about the resistor. I've talked about how we use Ohm's law. And now this is our image of the resistor in the complex plane. So let's go to the next one. Okay, so if we go to the next one here, I'm going to do the exact same thing. But now I'm going to use the inductor. So what did I call this up here? I said AC resistors. So I'm going to say AC inductor. So I'm going to keep moving along that same direction, right? I want to move along that same direction. Okay, so let's go do that. So if I look at what I did before here, I start off with an inductive circuit. Here I go. I'm going to try to do exactly the same. So I have an inductive circuit in the time domain. So it looks like this. So it has a value of Vs, and it's an AC. So now I have a pure inductor, no internal resistance. So what am I going to do? I'm going to do what I did before. I'm going to go in and I'm going to convert that into the complex plane. So here I go. So now I'm going to create a phasor circuit, right? So now I'm going towards a phasor circuit. And so that means I have what? I have a vector circuit. And when I look at my inductor, that inductor is now going to have a reactance, which we're going to call XL, right? That's what we want. We want this guy to be XL. And so now what I'm going to do here is that I'm going to do the exact same thing as before. I'm going to say that, guess what? I have a current here. I have a current here. This is what I call little IL. This is what I call big IL. So what do I want to do? I want to go in and I want to do the exact same thing. So as I do this thing here, that means I got to apply KVL. So if I apply the same process as before, what does that look like here? Well, so just to make sure that we're clear, I've already said it, but I'm going to say it again. I now have not a circuit, but I have a circuit in the complex plane called a phasor circuit here. So here I go. So now I want the ratio of V over I. So I'm going to come in and I'm going to apply KVL. So that means here is that in the phasor circuit, it should be, maybe I should do it differently. In the time domain, we know that the circuit should be Vs equals to VL, but wait a minute. This is this thing here. Okay? So now I want to put this into the what? Complex form. Right? So now I'm going into complex form. And I'm going to convert everything into polar vectors. Very, very similar here. I know that this guy has to be V source, and this guy's now VL. So what that means in this case here is that this VL, we know in the complex form here. So remember, when I say the complex form, I'm taking what? I'm taking a vector. It's going to have an amplitude, and it's going to be j omega t here. So then I'm going to go in, and I got to stick that guy into my circuit here. So here I go. So in this complex form, I'm now going to keep going in this direction. So this tells me here that I'm going to have what? Vm e to the j omega t. But now I got to take the derivative of this guy. So now I got L and I got the derivative of this guy. Of what? Well, in this case here, it has to be, what am I doing? I have to take the derivative of the current, but the current is really the current of the inductor times e to the j omega t. Right? That has to be the current of the inductor in this form here. So you know what? I'm going to run out of space here. Okay, so I think what I'm going to do here is that I'm going to move this down because I don't want to keep writing multiple lines. So I'm just going to move it right here. So if I do that, then look what this tells me here. If I look at this side here, I have to bring down a j and an omega term. So then I'm going to get j omega times L. Then I'm going to get IL e to the j omega t. Okay, so now I have that. So check out the two terms here. Look at this term. Look at that term. Look what happens. What did they do? The j omega t term cancels out. So now what I'm going to look at is that I'm going to say that if this is truly Ohm's law, right? If I look at this in the language of Ohm's law, so then that means here I got to come in and I got to do the following thing. I'm going to look at the ratio of what? VL over IL. Remember VM, because the source is parallel to the inductor, they must have the same voltage amplitude. And now look what's different here. What's different is that this is J omega L. This is huge. And what you're seeing here, which is really important here, is that look what I'm getting here. Look what I'm getting here. I'm getting a J, which is a vector in the complex plane, of course, and I have a frequency dependence now. Now, remember what I said. One of the most important things that we are aware of here is that anytime you see J in the complex plane, your job is to immediately put it into Phasor form. It has to be in polar form. We know that that guy has to be there. So what this really reads here is that I replace this. This now is omega L e to the j times 1/2 pi. So what do we call this? Well, that's one way to look at it. You know what? I'm going to do this slightly different. I apologize for this. I'm going to move this back in. What I'm going to do here is that this here says that it's J times XL. That's what Ohm's law says. There's some reactance. And then we reinterpret this like this. We want it in polar form, but for right now, we should define a term XL. So right away, what we're seeing here is that there's the inductive reactance. Remember what I said about Inductive reactance. The inductive reactance is the AC resistance, right? So this becomes the AC resistance. And I'm going to put that in quotes here because it's actually more than that, but we'll leave it for that. So now that I have that, we see that there's two things here that really happens here, right? The inductive reactance, we define this as XL. And of course, we see that this guy is equal to omega L. Okay, and another thing here is that now e to the j times 1/2 pi, what you're seeing here is that this term right here is the amplitude. This term right here is the phase. And the phase comes about because the inductor voltage has a derivative term. So now let's go look at each of these terms, trying to do it exactly like we did before. So the first thing I want to talk about is that I want to talk about the reactance amplitude. XL. So now you're really seeing something different. When I look at the units of XL, well, that's a unit of volts divided by a unit of current, which is, of course, ohms. So the reactance has units of ohms. And if I plot this thing, there's something quite interesting. So now, if we plot X of L versus omega, what you're seeing here is that you're seeing what? If I plot this thing, we're immediately seeing that XL, which is omega L, you could see that this guy is linear, right? Where the slope of this guy is the inductance here. So what does this thing actually means? What we're finding here is that I would say this. So physically, what does this mean? Well, the first thing that I would say here is that the inductor, right? The inductor sees very well the changing of sees the changing of current through it. So in other words, again, here's my inductor. So you could imagine that I have a coil, right? And here's my coil here. That doesn't look very good. Let's say that I draw a cylinder. So you could imagine that we have one of these coils, and then we have all these turns of the coil. So there's a wire that comes out, and there's another wire that comes out. And so what it's seeing here is that you could imagine that now I have current coming through here. IL, and of course I have current coming out through here. So what happens here is that as soon as you try to change the current of the inductor, what it does here is it's going to produce a back EMF field. And remember, there's an induced current when you do that. And that induced current will determine the voltage that actually comes about this. So what you're seeing here is that the inductor sees the changing of a current through it. As a result, what happens? It produces a back EMF. And I'm assuming you know exactly what I'm talking about. And that back EMF then impedes the flow of current. And what do I mean by that? Well, let's think about the current here. Okay. Let's say that I have a current going like this. And let's say that IL is increasing. You know, I'm going to run out of space, so I'm going to do this different. So I'm going to say that this is my current IL. And what I'm saying here is that this current here is increasing. So if it's increasing, what is the back EMF going to do for this coil? The back EMF is going to come in and it's going to try to reduce that current flow. So now I have a current that's induced. So if I try to change it really quickly, that induced current is going to flow the other way. So what this induced current does here is that it impedes the flow of current. It's not a resistive element. It impedes it. And so here's the crazy thing here. So what this implies here is that if I have a higher frequency, of the AC source, then that means I'm going to get a larger induced current, which then this guy does what? It acts like a resistor. It acts like a resistor. And pretty soon, if I really change that high enough, you can get this thing to act like an open. So if I have a larger induced current, it acts like a resistor. At times, it will be, an open. So if I have low frequency, then I'm going to have a small inductive reactance. Which then means that it's almost acting like a short. It only acts like a short when omega is equal to 0. But if I have high frequencies, then I'm going to get a large inductive reactance, and as a consequence, this will act like an open. So you can literally replace this guy with an open in the circuit. And that's because as you're changing the current very, very, quickly back and forth, it's got to kill that thing. Okay, let's go to the next thing. The next thing that we want to talk about is we want to talk about the phase. And so the phase here is different now. And the reason why the phase is different here is that when I look as the current goes through the inductor now changes the phase of the current. That's not true the way it was beforehand. So here we go. So what we're seeing here is that when the current goes through the inductor, it changes the phase. Okay, it changes the phase of the current, right? There's a phase change. There's a phase change. And so when we go and we look at this thing, what does it look like? Well, according to what our relationship says here, what we're seeing here is that the voltage um, the voltage source has no phase. And how do we know that? Because we said that the voltage source was Vm e to the j omega t. Okay. The current, though, the inductor current has developed a phase. And so when I compare that phase to this guy, and I got to look at the right-hand term. So look at this thing. We know this guy has no phase, but when I look at this other side, look what I see here. So look how I wrote this. I'm going to write this two different ways. I'm going to rewrite this thing right here. What am I really, really seeing here? I'm seeing this. I'm seeing that this guy on this side is going to be J omega L times IL. So if the source had no phase, this guy has a phase now. And when I look at this phase, I can write this as omega L times e to the j pi over 2 times IL. So that means that IL picked up a phase of pi over 2. So then, how do I write this here? So the way I write this here is that what this tells me here is that because this is a positive phase, okay, this guy here is a positive phase. Okay, so because this is a positive phase, the current wave is shifted to the right. In other words, if I go and I draw this thing, I'm going to do the exact same thing that I did with the resistor. So when I look at these phases, what am I actually seeing here? What you're seeing here is that I have my source voltage again. So my source voltage, or the voltage of the inductor, let's say looks like this here. So this guy is the voltage of the inductor, which is of course the voltage of the source. So when I draw my current, note that the current is out of phase by pi over 2. So if we look at this thing, right, if I call this 0, and this is 180, all right, or I could just say 2 pi, you could see then that I need to be right smack in the middle of this thing. This guy is pi right here, so pi over 2 is over here. So that means that the peak of the current is starting right here. So that means then when I look at this thing, it's actually looking something, God, this is always hard for me to draw. So then this guy has to have a peak right here. So then it's going to look something like this here. Let's see if I can draw this thing. Yeah, this thing's not going to go very well for me. And so what you're seeing here is that there's a if I want to say a delay, that delay is pi over 2. So what we're seeing here is this, that in this case here, that the voltage, right? The voltage VL leads the current IL by 90 degrees. And in the old days, okay, so then if you talk about, funny things here, the old days, they labeled voltage with an E. That's what they did. So they came up with an acronym. The voltage leads the current, or Eli. So people use this statement that the voltage leads the current as Eli. So if that makes you remember it better, that's fantastic. But here's what we find here. Now we have a second complex variable. Okay. Now, in the complex plane, the inductor vector looks like XL, which is J omega L. So that means when I look at this vector, it looks like this. So if this is J, you could see that I now have a vector that's on the vertical axis. And the important thing, remember how I talked about there's that positive shift, right? Well, this is in the positive direction. And this guy has a magnitude of omega L. Well, I should write it like this, J omega L. But this is a vector. And so when I look at the resistor has no J component. It's only along the X direction. So when I look at X of R, it only has a real part. Which then brings us to our next thing. So that's, now we have two phasors now. We have a phasor for the impedance of the resistance and a phasor for the inductive reactance. So then we come to the next one. Now, the last one here is the capacitor. So let's go look at this guy and let's write this stuff down. Now, try to write effectively the same kind of thinking. Okay, so now I'm going to go to 3 here. And in 3, I'm going to talk about AC capacitors. Okay, AC capacitors. So that means I got to go in and I got to start writing this. So now what I'm having here is that I have a capacitive circuit. And I want to make this as simple as possible. So here I go. I have a source in the time domain. And of course, we have a current IC. Do I want to do it this way? There's lots of ways to do this. I think, well, let's just stick to the same way. It would have been nicer to do a current, but let's just leave it there. So if I do it this way, what I'm going to do here is that the first thing I got to do is I got to convert that into a phasor circuit here. So look, so here I come. So now I'm going to come in and I'm going to say, I want my phasor circuit. Right, there's my phasor circuit. So then if I was to really write this properly, I would come in here and I'd say I could write this as Vs. I could have also written this as J2 omega T. That's the exact same thing. And now everything is a complex vector. So that means here, I know that now I have a complex current. And in the language that we were talking about before here, I think what I used here is that I just used the X symbol. Did I use the X symbol right away? I can't remember what I did. I think I said that we now have something called the reactance, right? And this would be the capacitive reactance. So my job here is to calculate what XC is. Okay, so here we go. So now I'm going to apply KVL. And if I apply KVL, of course, in the time domain circuit, we write this as Vs equal to Vc. Man, I'm not really liking this. It doesn't matter what I like or not. And then I go into the complex form. And when I calculate this in the complex form, we know that this guy should be Vs equals Xc times Ic. And now I put this into the complex form, and then I know how to write Ic here. So then what this means here is that if I now put this into complex form, you know what? I ran out of space last time, so I'm going to move it over here. So then I would write this as Vs e to the j omega t. And this guy's going to be Xc. And then we know that this guy's got to be Cs hat of Ic e to the j omega t. Here, give me a moment. I'm not getting what I think I should be getting. You know, I'm gonna do something, and I apologize. I should have stuck with what I thought I was going to do, and I'm gonna come back and I'm gonna change something. Sorry about that. It doesn't. I'm gonna get a mistake, and I'm gonna change my voltage source into a current source. Okay. I know this is terrible. Sorry about that. So this should be my source current. And then I'm going to come back in here and I'm going to change my I source like this. It's just going to make it cleaner here. So then what I'm really looking at, I'm not looking at KVL, I'm looking at KCL. And in KCL, what you're finding here is that I have that I source is equal to the current of the capacitor. So then when I go into complex form, damn, I really screwed up. I should have thought this deeper. I got stuck in the other two. Sorry. So then in complex form, it should be I of the source, which has to be the same as the current, right? So I can write this also, this is the current of the capacitor because they're the same. But then I write in here that this is this guy of Vc e to the j omega t. Okay, this is right. So when you do that, by the way, I messed up again. Ic e to the j omega t. So now if I take the derivative of this guy, look what I get. I get j omega c Vc e to the j omega t. And the thing that you want to pay attention to is that look at that V and C have switched roles here. So when I look at that, again, look at the j omega t term. They cancel out. So then I go into Ohm's law form. And if I do that, I then get VC over IC, and then I get a term that's J omega C over 1. Okay, so a couple of things that we should think about here is that when I do that, the one thing that we should look at here is that as soon as I do that, you could see that there's a game changer here, because now I got J omega and C. Just like before we had J omega L, but this is in the denominator. So the first thing I got to do here is that I have to get that complex J out. So what do? I multiply it by its complex conjugate. So then I get minus J times J is 1. So what I'm really seeing here is minus J over this here. And then we now define this guy. And the way we define this is we define this as minus J times x of C. Okay, x of C. And so what's the big deal about this thing here is that you could see that x of C has frequency that's different here. So if I look at that minus J, note that that means if I was to write this into Phasor form, it would look like this here. I would have 1 over omega C. So what this guy tells me is that this guy's what? This is the amplitude. And then I'm going to get a complex function that instead of 1/2 pi, because I have that negative, this is going to be J to the minus 1/2 pi. And this guy right here is the phase. So let's go interpret this. So what we're saying here is that now I have my capacitive. Ooh, I spelled that wrong. Reactance, which is my AC resistance, which is XC, and in this case, it's 1 over omega L. So there's something going on differently. So let's go look at that. So the first thing I'm going to look at is that I'm going to look at the capacitive reactance amplitude. So this is the first thing that we want to look at here. Well, for starters here, if you look at this guy, right, X of C, again, it has units of voltage over current. So it has units of ohms. So it acts as a resistance. But resistors, what do? They cause heating. Inductors don't cause heating. What they cause is that they cause impedance of current flow because of the back EMF. That's how we get this resistive type behavior here. But that is not true in this case here. So what we want to do now, to get a sense of what we're talking about, we need to go plot this guy versus omega. And if you look at this plot, what does this plot look like? You're seeing that at low frequencies, this thing is massive. So when I look at the flow of this guy, at low frequencies, it's infinite, and then it comes down and it goes as 1 over frequency. So you could see that at high frequencies, it's very low. So at high frequencies, we're seeing here is that at high frequencies, it acts like a short. But at high frequencies, at low frequencies, acts like an open. I should have done this with the inductor. I didn't think about that. So the question is, what the hell is happening? Why would it do such a thing here? Well, physically, what do we know about a capacitor here? So what we know about a capacitor here is that it does something like this here. We know that a capacitor has a limitation on how quickly you can pull charge from its plates. So how do I say this here? So I would say that the capacitor in AC situations sees the changing current as either adding or pulling off charge from its plates, of course.
Carlos, I think there's an error on the line above where it says capacitive reactance equals XC.
Oh yeah, you're right. It should be a C. Thank you. And so what you're seeing here is this. So if I have a plate, okay, and let's just for the sake of argument, let's say that we have a fully charged capacitor here. The only way you can have a fully charged capacitor here is if the time, so if I look at the time has to be, let's say, at least 5 tau. So if it's 5 tau, then that implies here that the cap gets fully charged. Now, if all of a sudden you tried to pull charge off of this very, 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 very quickly, it's not going to work. Because the capacitor essentially has some type of inertial type quality. That means here is that its changes to voltage don't occur too fast. So what we find here is that caps have an inertia quality because VC of 0 minus cannot change instantaneously. Those voltages have to be fixed here. So you could imagine if that's the case here, if I have a fully charged cap and this situation here, what you're going to find here is that it acts like an open. And if it acts like an open, then it acts like acts as it has infinite resistance. In other words, look, it acts like an open at the very top. But is it acting because it's generating heat? Right? Because resistance, if the resistance is really high and we're thinking about DC resistance, that's sort of like the generation of heat, right? You're converting electrical potential energy into into heating. But in this case, that's not what's happening. It's just that it's hard to pull charge off very quickly. And therefore, this implies then that if XC is equal to infinity, to infinity, then it acts like an open. Oh, dude, I'm going to have to get out of here because I have to go to my lab here pretty soon. I didn't realize that I was over my time by 1 minute. So